Sounds like you're getting on well with the LDO. You got it stable anyway, I think.
Yes, I got it stable in the DC sweep. For the AC sweep, I got only around 47 degrees something, so.
That's still good, yeah, that's fine. That's actually usually the guideline is maybe 45 is always usually a good guideline. It's kind of just rule of thumb. 60 is very good. Anything over 60 is very good, but 45 is a good minimum to go for. And 30 is kind of an absolute minimum. It's usually what people tend to go for, So 30s, so 40, whatever it is, 47 is pretty good. So I guess the next thing to do is try and add a load to it. So, because usually the case where you have no load is the worst case. Now when we see how much current you can get out of it. So I'm gonna show you. Do you want to share with me there actually, and I'll see if I can show you how to add a load to it.
Yep.
Okay, so if you do, let me see, maybe I can do it for you. So let me see, can I bring up your library? Oh, I can. So in here, so if you go to, I probably open another window, or the different desktop. The browse there. There's another window open there. No, that's your radar plots. I again. What I want to do is add a switch actually. So if I browse here. Oh, it must be on a different desktop. I can only see your schematic desktop. Can you, that library window, can you drag that onto this desktop? See, if you hit the browse button there.
No, I can't seem to open the library as well.
Okay. Might need to restart Cadence or something, but yeah, so no, I'll find it manually. So if I find it manually, so if I go down to, I think it's in simulation, this one here. And then if you break that down, go down to, I think it's just called switch. Yeah, that guy. So you see the way you've got an R on and an R off. Change the R on there to be maybe 0.1 of an ohm or something, or 0.01 of an ohm. And then you see the VT there, change that to be, you could say 0.5 volt. That's all we need to do with it. So if you can hit enter on that then. So that then should give you a switch that you can place somewhere. It's not working, is it?
Yes.
Hit enter on any one of the. So we hit I again there. And then just click, maybe I can do it here. Click, press enter now. That should it's not bringing up the, you might need to restart Cadence actually if your library manager is not coming up and stuff like that. So you might need to do that. I suppose I can show you. I'll show you on my end, sure. They open up a blank schematic. Blank schematic subview. All right, I'll share it, Jen.
Yep.
You can probably, if you restart Cadence, that probably will fix that. You can find sometimes you get funny stuff going on. So you have like G&M. Yes, you have. I'll draw a circuit like it very briefly. So just so you know, so there's no confusion. So okay. All right, so then you've got a define. So you've got sticking the resistors there as well. Okay, so now don't worry about the type of resistors. I'm only just putting these into for illustration. So that goes to VDD. Then this is your feedback. Here's your set point, and that goes to ground. So the next, so your output node then is here. So the next thing we want to do, so this is VDD obviously. So the way the LDO works is that it just steps the voltage down. It varies the resistance of this guy, such that if there's a current load here, it varies the resistance of this guy such that the voltage here stays constant. And that's what the loop is doing. So the next thing to do in your case is actually to add a current load to it. So to do that, you can go into the simulation library, go down to, I think it's iSource, this one. Now we can use an ideal current source, but ideal current sources are kind of funny, as in, the way I think you've seen this before, the way this, so this would be, that's ground here. So they're a bit funny. So that's where the switch comes in. That's what I was trying to do there. So I'll switch here. So the switch is basically connected like this, and then you can connect this. So you see this switch here. There's a voltage terminal across it, and then there's the switch here. So what you do here is we queued on it there. So if we set the R on, it's the on resistance of it to something small, and we set the threshold voltage then to be something like 0.5. Now the threshold voltage is kind of important. It's where if you put a voltage here across this, to see these pins here, if it's greater than 0.5, the switch will turn on, and if it's less than 0.5, the switch will turn off. So that's all that's doing. So you can create another node here, pin or a V load or something, and you can drive that. You can drive that with an actual voltage source. But because because these are kind of funny, switches are funny, you probably want to do something like something like this as well. So if we were to take our V load here, we did something like this. So this is the V out here. So now if we'd say V load 2 here. So if you drive them with kind of the inverse of each other. So if I show you what I mean by that. So if your V load 1 looks like this. So if this is the VL1, the VL2 then should look something like that. Do you know what I mean?
Yeah.
So that what that means is that when this is connected, when this is connected, the PMOS here will have to provide the current. It'll have to flow down through here. And then when this is disconnected, the current will just come from VDD. So it just means that if you don't put in this switch here, kind of funny things will go on. You'll probably see like millions or maybe billions of volts here, something like 10 to the 12 volts here appearing because of what a current source does. So if you do something like this, you can see. So if you were to say, what you do here is if you take your circuit that you have that you've stabilized at the moment and without changing anything, and if you step a current load into it, so you can start off with something like maybe 1 milliamp, and see kind of how far you can go, and then once you have a number, once you have kind of the number as far as you can go, then you should look at stability analysis over corners, over the process voltage temp corners with it, and that will give us an idea of what kind of a current load we can get out of it. So 1,000 microns, it probably should work with something like maybe 10 milliamps or something. Would it work with 10 milliamps? It should work with some few milliamps anyway. So you could try something like that. Maybe try 1 milliamp, try 2 milliamps, and so on. If you wanted to simulate the worst condition, what you could do is, in your use file, you could pick, just to save you having to sim them over all the corners, you could try picking, say, the slow models, the SS models, with, say, low voltage. So that would be like 2.25, I think we said, and to a high temperature. So if you didn't use SS 2.25 volt, and 125 degree temperature, that should be your worst case corner. So if you set that and you use that to see what your load current would be, then that'd be a good sort of benchmark, because if it works at that corner, it should work at all the other corners as well, you'd expect. So does that make sense to you, Hi?
Yeah.
Want to give that a go?
All right.
Okay, sounds good. So I'll leave you to have a look at that. So
Okay. Thank you, Mark.
all right, no problem. Hi, talk to you again.
Yeah.
Bye now.